Right, good evening, everyone. I hope you had a wonderful weekend. Right, we want to continue with our discussion on loci, but this time we are starting a new topic on chems. Right, we are going to focus on the chem mechanisms, which basically make use of uniform velocity or uniform speed. Like I said, we are going to focus on chems, but it's still under the concept of loci, so I'm not going to explain the concept of loci again. Like I said, it's about the path which is followed by the movement of a point in a defined manner. Right, by definition, when we look at a chem is a mechanical device used to transmit motion to a follower by direct contact. The driver is called the chem or the chem disk or the chem profile, and the driven member is called the follower. In a chem pair, the chem normally rotates while the follower may translate or oscillate, right, moving to and from, up and down, and so forth. Right, so what are the applications with regards to chems? A chem is a rotating or a sliding piece in a mechanical linkage used especially in transforming rotary motion into linear motion. It is often a part of a rotating wheel or a shaft that strikes a lever at one or more points on a circular path. Right, just to explain this concept, you find that in manufacturing industry or packaging industry, right, because of technology, right, you find that certain mechanisms are put in place, right, in order to eliminate the need for human input, right, in filling bottles, in filling containers, and so forth. You'd find that there is a specifically designed disk which is used as part of a link mechanism in order to control the amount of products that are supposed to be filled in a container, in a bottle, and so forth. And that can only be facilitated by what we refer to as chems. So a chem is useful in a number of ways. Like you talk about in the automobile industry, in a car, you'll find that there is what we refer to as a chem shaft, okay, which facilitates the movement of pistons up and down and so forth without anyone doing that. So those are some of the applications that we relate to with regards to chems. You would also realize that when we are looking at a chem, right, say in the distribution of water, right, in cases you have got a drought, the chem can be used to operate, right, the water distribution mechanism or system, such that it would open slowly, right, and fully open, and slowly close, and fully close. And that is facilitated by what we refer to as a chem disk. Now, our focus is on the radial chem, right? There are basically about two main types of chems, right? That is the radial, the cylindrical, right? You'd find that also there is a flat chem, but not used as often as the radial or a cylindrical. So we want to look first at the radial chem, okay? Right, a radial chem converts a rotational motion into a translational motion of the follower. The displacement of the follower is determined by the chem's profile. The profile here, it means the specifications or the guidelines that are required in order to come up with that displacement graph. We shall talk about that in terms of our illustrations. Thus, a chem profile is generated from a displacement graph defined by a set of locators or guidelines. Remember, we want to look at now the construction aspect of it so that it bears the practical aspect that we want in EGD. As always, right? I would not forget these words. I hear and I forget, I see and I remember, I do and I understand. So I want you to pay special attention today as we start this new topic. Yes, it is related to the previous topic that is on the helix, but it's now a different scenario altogether. Remember the helix, we said it's part of the big family of loci, right, which looks basically at the locus of point, the path which is followed by a point. So we are going to look at that, but now specifically with regards to chaos. So enjoy the lesson and good luck. Right, okay, so here we are. Let's remove this. Right, in terms of the information that is given, the detail of a wedge-shaped follower, right, for a disk cam in its starting position. I just want to explain, right, if you look at this, right, this is what we refer to as a wedge-shaped follower, right? Remember, a follower is the one which is in contact with the disk cam, right? In this case, you will find that it will be pushed up and down in terms of its movement, but that movement up and down is what would get the job done on the other end. So it's not necessarily the movement, the up and down that is critical, but as it moves up and down, following the contours of the disk cam, you'd find that a specific job is done. Right, so if we are talking about a wedge-shaped follower, just know that it is the one which is pointed like that. Right, we have got wedge-shaped follower, we have got roller follower, we have got flat-shaped followers, but the ones that are commonly used are the wedge-shaped, which is pointed, and the roller follower, which we are going to talk about in later lessons. Right, the minimum distance from the camshaft center to the cam profile is 14 millimeters. We shall look at how that can be factored in given the information that we have right now. Right, a camshaft, right, you find that the camshaft is diameter 16. Right, a wedge-shaped follower is used. I've already indicated that this is a typical example of what we refer to as a wedge-shaped follower. Right, then rotation, again, we are going to look at rotation, right? In this case, it's anti-clockwise, and just like we looked at the helix, right, the rotation which has been specified, it has got implications with regards to as to how we are going to move, okay? Right, the type of motion, the disk cam rotates at constant velocity. Now, when you are talking about constant velocity, you are talking about uniform velocity, uniform speed in a specified direction, imparting the following uniform motion to the wedge-shaped follower. Right, from 0 to 60 degrees, the follower is dwelling, right? Now, these are some of the terminologies that are used in terms of cams. When the follower is said to be dwelling, okay, right, or it's said to be stationary. So the other term that can be used in place of dwelling, right, dwelling, right, it is stationary, okay, right, it is stationary, right, it is neither rising nor falling, okay, it is maintaining the same height, though the cam is rotating, but the follower is not being pushed up nor pushed downwards. It is maintaining a set height, okay? So that way it is said to be stationary. The stationary, it means that it is not moving up or down, okay? Right, the other term that can be used with regards to that, it is dwelling, or right, it can also be said it is resting. Okay, so these are the three terms, right, that can be used to describe one thing, right? It is dwelling, it is stationary, it is resting. It means that the follower is not rising, it is not falling, it is maintaining the same height. So I want you to take note of that. Then 60 degrees to 150, the follower falls, right? 30 millimeters. When it is falling, right, it is descending, okay? So you find that the other term that can be used, right, it is also what? Descending, which means it is falling, right? From a specific height, you fall or you descend, you go down. Right, 150 to 240 degrees, the follower falls to a minimum, okay? Right, we shall explain what do they mean when they talk about minimum and when they talk about the maximum, okay? Right, then 240 to 360 degrees, the follower returns to its original position. Remember, it started from a dwelling position. It wasn't falling, it wasn't rising, right? It maintained that level. Then it began to fall, okay? Right, it fell twice, right, for 30 millimeters and then to the minimum, okay? Right. Then once it has reached the lowest point, it rises again. Right. Okay. So if we are looking, right, at a displacement graph, right, we shall look at what the concept of a displacement graph. But I just want to sketch a picture. Right. Let's suppose this is what we are talking about, right, from 0 to 60. So if we say this is 0, this is 360 degrees, like that. Okay. Right, so from 0 to 60 degrees, you indicate like that. Then from 60 to 150, that's 30, 90, 150, it falls, right? From here to there, 30 millimeters, then you join like that. Then 150 to 240, right? That's 150, 180, 210, 240, okay, which would be somewhere here, right? Then it falls again, right? Then from here, it rises to the original. So this is dwelling, right? It falls 30, then it falls to the minimum, then it rises again. But don't worry about this. We are going to look at this in much more detail. Right, okay. So we have got, then the instructions are as follows: using a horizontal scale of 30 degrees equal to 6 millimeters and a displacement scale of 1:1, draw the displacement graph for the given motion. All right, draw to scale 1:1 the given wedge-shaped follower in its starting position. So we are given this is our wedge-shaped follower. All right, if you look at that cross here, it indicates the position or the center of the shaft. Now, the distance from here to there, which is 64, would give us the maximum diameter. Remember, we are given that the minimum distance from the camshaft center to the cam profile is 14. So we need to find that. So let's start. Right, I'm going to do this so that this would be practical in terms of our approach. Right, I'm going to draw a faint vertical line like that. All right. Then another one, right, like this. Now, we are told that the camshaft diameter is diameter 16, so we are going to measure 8 millimeters, right, as our radius, like that. Then draw a circle. draw a circle, radius 8, diameter 60, like this. Right. So that's the first thing that you need to do. All right. You draw a circle, radius 8, diameter 60. Once you have done that, the next thing is to hatch this. This is the cam shaft. You hatch this. Right. So the moment you have drawn the cam shaft, right, like this, right, you outline it, then you hatch it, okay? Then the next thing that we want, right, we need now to define the minimum diameter, okay? Right, that is the minimum distance from the cam to the cam shaft. Right, from the cam shaft center to the cam itself. So you are going to measure from the cam shaft center 14, right, like this. Right. Then you draw. Right, this could be relatively thicker than a construction line, but not as thick as an outline. Right, it could be thicker than a construction line, but not as thick as an outline. Right, the next thing that we want, now we can now draw this information which is given from the cam shaft center. We need 64. 64. It's like this. You can draw a faint line like that. Right. Then you have got the height from here, right? We also need this 10 millimeters, right? Take this one up. Take this one up as well. Right, then at 60 degrees. Then from there, we measure 45 in terms of millimeters from here to there. Once you've done that, you can even outline the follower. Right, so that is the follower in position, right? So what we have from here to there, we refer to this one as the displacement. That is the total displacement, right? At some point, you'd find that the follower would drop to the lowest point. This is the lowest part of the cam disc, okay? So it would move up and down along this line of action, okay? Right, this point at some point would be here. That would be the lowest. So we draw a line from here, right, in this direction, like that, okay? Right, so once you have defined this point and also have got that center, you can as well draw the maximum diameter, like this. But it's not outlined. To make sure you are able to see. right, like that, okay? Right, so we have got, this is referred to as the maximum diameter, right? Then the other thing, so what we have done, we have defined the minimum diameter, so you can tick there, right? The minimum diameter, which is the distance from here to there, which is 14, right? We have also defined the camshaft diameter, right? Which is this camshaft diameter. We have also drawn the wedge-shaped follower, which is our wedge-shaped follower as given, right? The moment you have done this, you can also come here now and show the center line. That's the center line. That's the center line as well. Okay. Right, so from here to there, that's also the center line. Right, then from there you can divide this one into 12 equal parts. Do not use the space in between the camshaft and the minimum diameter. Faintly. There you go. Right. So this one, it's our 0.0, right, to 360 degrees. Right, let's define the rotation. Rotation is anti-clockwise. Right, you factor the rotation in between this space, right, like this. Come here, you show, just darken one end like that. It shows the rotation, okay? Right, so if the rotation is anti-clockwise like that, right, the first point here is 30 degrees, right, which is 60 and 90 degrees, 180 degrees, and 270 degrees. Right, you oppose, if the direction is anti-clockwise, you number in a clockwise direction, okay? Right. Then we look now at the instructions, right? Using a horizontal scale of 30 degrees is equal to 6 millimeters, okay? Right? We want to find the length of our displacement graph, right? If we look at it, we are told that the scale is 30 degrees is equal to 6 millimeters, like that. Right, what about if we have got 360 degrees, right? How many millimeters are we going to talk about? Right, of course, it will be higher, right? It's 360 divided by 30 multiplied by 6 millimeters, like this. The answer that we'll get, 360 divided by 30 multiplied by 6, right, we'll get 72. Right, so the 72, you would require the distance from here to there. The distance from here to there, which is equal to 72. Just find some space that you mark here. And you also mark there. So that is the distance. Then you take this one up. Take this one up, okay? Right, you can make this one slightly darker than a construction line in terms of the box for the displacement graph. Let's just make this one slightly darker. Not as dark as an outline. There you go. Right. So that is the box that is going to house our displacement graph. Once you have done that, you divide this box into 12 equal parts, the same as the number of divisions this side, like that. I'm going to do it at 5mm intervals. Connect to this. Right, there you go. So the number of divisions, right, we have got from here, that's 0, right, which technically is starting at the top there. So we can actually, instead of writing here, we'll say this is 0, right, and 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. Then we write here 360 degrees. Right, okay, so we are going to start at the top by dwelling, then falling up until we reach our stage, okay? Right, we take this, project these ones up, right? That's 30 degrees. Remember, the 6mm, which are equal to these divisions, are representing 30 degrees. Right, there you go, okay? Right, so we have got the distance from here to there. Basically it's 6mm. From here to there is 6mm. Let me check if I can increase the light. Right, just to increase the clarity of our diagram, like that, okay? Right, so we have got from here to there, that's 30. Then this should be 60 degrees, right, according to the specification. Then from 60, we go to 150. So we have got 90, 120, and 150 there. Then from 150 to 240, right? 180, 210, 240, which is there, okay? You need to specify all that, okay? Right. What are the specifications from 0 to 60 degrees? The follower dwells, right? So the follower does not rise, it does not fall, it basically dwells. So I'm going to indicate by way of a line like that. Right, so from here to there, it is dwelling, it is not falling, it is not rising, right? So from this point to that point, the follower dwells, okay? Right. Then from 60 degrees to 150, right, 60 degrees to 150 degrees, right, the follower falls. So you go to 150, you measure 30 millimeters. Right, let's measure 30, which is here. Then you connect with that part. We have got that. Then from there, right, 150 to 240, which is up to there, the follower falls again. Right. So it will fall 240 to the lowest point. Then 240 to 360, the follower returns to its original position. So it's going to rise again like this to the original like that. Now, what we want to do, right, is to outline, right, the path which is followed by the follower on the displacement graph, and you outline this. There you go, okay? Right, so from here to there it's dwelling, then it falls up to 30 millimeters, right, through to 150 degrees, then it falls again to 240 to the lowest point, which is the lowest point in contact with the minimum diameter. Then from there, it rises back to its original position, which is 360 degrees. Right, once you have done that, right, you can now label, right? You can label the chem displacement graph. Let us just create guidelines. Label here. Right, at the top, you write nicely displacement graph, okay? That's the displacement graph. Then you write here rotation in degrees. Then you also indicate the scale, right, which is 30 degrees is equal to 6 millimeters. You copy the way it is given. Yes, you can simplify, but preferably just copy the way it is given. Right. Then you also need this label on the vertical one. Right. You write displacement in millimeters, or you write displacement 1:1. What it means basically is that the 1 millimeter that you measure on this side is representing the actual millimeter of the movement. So this is what we refer to as the total displacement. So displacement, right, the vertical displacement is in millimeters, okay? 1 millimeter here represents the actual millimeter of the actual movement of the follower, right? So in terms of the labels, these are the key labels that you would require. Displacement graph, rotation in degrees, the scale 30 degrees is equal to 6 millimeters, then displacement in, right, in millimeters, or displacement 1:1 like that. Once you have done that, you now can project, we refer to this line where the follower is going to move as the line of action, okay? So this line, right, this line is referred to as the line of action, right? So as you project from the displacement graph, you direct the projection to the line of action. Remember, you don't have the actual follower here. You have got information which is representing the follower. So that line here is referred to as the line of action, okay? Right, so let's start with the first one, right? From 0 to 60 degrees, the follower is basically dwelling, right? When it is dwelling, when it is not falling, when it is not rising, right? It is said to be dwelling, or it is said to be stationary, right? Stationary, like I explained, is not moving up or down. Dwelling, it basically is maintaining the same height, or resting. Again, resting is not moving up or down. So in that scenario, right, you take your canvas like this, right, using the projection here and the center of your camshaft, right, from here to there, you describe an arc from 0 to the same number of degrees that are required. In this case, it's through 60 degrees like this. You outline that. That's not going to change. Okay. Then after you have got, you project from here, that's the to the line of action. You project from here to the line of action as well, right? You project from here. Let me deal with these lines first, right? So you have got that to the line of action, then you swing, right, through to 90 degrees. Then you do the same, right? So that's 120. You swing, this is 120, right? Then this one, this is 150, right, like that. Then after 150, we go now to 180, 210, then. So let me project again. Like that. Take this. That's 180, you swing, cut 180, then 210. The last part, which is here, but which is 240, if you swing, you will basically come here, which is the point that you want. Right. Then you connect these points. This is 240, this is 210. You connect on the outward part like this. Connect like this. There you go. Right. So this is part of the chem discs that we require. That is part of the chem disc. So what is important with regards to chems, right? Make sure that you have got the displacement graph in position, and make sure you have used the right information. These are the guidelines that we talked about in our introductory parts, right? The locators that we talked about, and you project these ones to the line of action, from the paths of the displacement graph. Right. Now, I'm now beginning to rise from here up until 360 degrees. Right. The process is the same. This is now 270. So you project from here, 270, which again is basically the same as, right, 180. Right, so this is 300. This is 330. Okay. So you start at this point. That's your 270. I'm going now in the different direction. Right. Then from there, 300. That's like this. Then from there, 300 and and 30, right, like this. Okay. So you have got 240. From 240, you begin to rise again, which you come here to 270, 300, and 330. Back to the starting position, which is 0.0. Okay. All right. Or 360 now. Right. So you connect these points. Connect this point faintly. Right. You connect this point faintly like that. Now, once you have connected that, the next thing is to outline that profile. That would give you what we refer to as a chem disk. Right, so you connect nicely from here to there. Right, so let me outline. Right, like that. There you go. But remember, when you are resting in terms of outlines, you rest at a particular point. Don't rest in between, otherwise you end up losing your mark. But I'm going to do this. There you go. And also connect from here. So there you go. That is our chem disk. Then you write nicely at the bottom or at the top, you write chem disk like that, or disk chem, whichever way that is appropriate. Right. So now, as this thing is rotating about the camshaft, but you'd find that it would force this follower to move up and down, right? It would force the follower to move up and down. At some point, when it is here, the follower will be right there, okay? Remember, the follower does not change its position in terms of here, right? It will still maintain that line of action. But what changes now is the pathway it is going to be in contact with the disk cam. But in doing so, you'll find that we'll have job done at another end. So this is a typical example of a chem disk, right? Where you have got to come up with the displacement graph as well as the chem disk itself. But let us look at another example, right? I see we still have got some time. But let us look at another example in terms of the chem. So I'm going to put this one away. Right, bring another paper. Now let's look at this. It's looking blade a little bit. We want page 2. There you go, okay? Right, so the given information, right, the center point of a camshaft of a wedge-shaped follower for a disc cam, right, that is the center point. Right, remember a wedge-shaped follower is the one which is pointed like we started. Right, this minimum distance from the camshaft center to the cam profile is 20. The moment you are given that minimum distance, right, you measure that minimum distance and draw a circle. So I'm going to measure here like that and draw a faint circle, but one which is thicker than a construction line. So you are going to stand here. Then you draw a circle like this. Now, we want to solve this problem as we read it, okay? Right, because certain things are not going to change with regards to how you are going to work on the diagram itself. All right, then a camshaft diameter 24, so radius 12. So I'm going to measure 12 millimeter, then draw a circle like this and outline this. The moment you draw the camshaft diameter, right, you know by now you hedge that part because it's a section. But you have cut the section or the shaft. Now what you are able to see, right, is a section. So I'm going to out hedge this part. Right. So that is the cam shaft, right, which is now in position. Right. Then a wedge-shaped follower is used, right? We don't have the wedge-shaped follower. We are going to look at the specifications. Then direction is clockwise. Like I said, if you are given the direction, you specify that direction in between here, right? You come, but just darken one end like that. It would show the direction. Right, so far with what we have done, you get a mark for this for drawing the camshaft and the hatching. You would also get a mark for the direction. You also get a mark for the minimum diameter. Right, then let's look at the motion. A cam disc rotates for 2 minutes, which is 120 seconds, to complete one revolution, which is 360 degrees. Right, at constant velocity, imparting the following uniform motion to the wedge-shaped follower. A rise of 70 millimeters during the first 30 seconds, right? A dwell for the next 20 seconds, a drop of 30 millimeters during the next 20 seconds, then a dwell for the next 30 seconds, a drop to the minimum. So what we can pick from this information that has been given is that the total rise, right? The total rise is 70, okay? So what it means is that the minimum point is here, so it's going to rise. So we need to measure from here going up 70, right? The total rise, that would give us the maximum diameter. So I'm going to mark here, like that. Then draw a faint circle, radius, not 70, but remember the radius is defined from a cam shaft center, right? So you take that, then you draw a faint circle like this, like that, right? Then instructions, using a horizontal scale of 120 to represent 120 seconds, right? So if we divide 120 seconds by 12, we find that each division is equal to 10 seconds, 10 seconds, 10 seconds. All right, and a displacement scale of 1:1. Right, so what I want you to do, right, you project this one like that. Then you also project this one like that. We are going to define our displacement graph according to that diagram. Label the displacement graph. Right. Draw to scale 1:1 the wedge-shaped follower if the starting position, if the height of the follower is 75 millimeters and the diameter is 10 millimeters. So the height of the follower from here to there should be 75 and its diameter should be 10 millimeters. Right. So what you can do, right, at this point, just measure 10 millimeters, which is either side, 5 and 5, like that. Then we take this one up, like that. We measure 75 from here, and mark it there. I'm not going to complete this. I want you to complete this exercise, right? Applying what we did together in our first task. But I'm going to give you the framework in terms of the displacement graph, okay? Right, remember, once you have defined the maximum diameter like that, you can as well divide it into 12 equal parts. Don't get into the space between the camshaft and the minimum diameter, just for presentation's sake. Right, okay. Right. Remember, the displacement is in rotation is in terms of seconds. So we are going to say rotation in seconds, it's not degrees. Right. Now, what is the scale? 120. Right. Let's look for a measurement that will give us 120. So from here to there. Right. So we are going to draw a faint vertical line, make it slightly darker than a construction line, but not as dark as an outline. There you go. Right, you can close this one slightly. Right. The next thing is to divide this one into 12 equal parts. I'm going to divide into 12 exactly. 10 millimeter intervals. The last point connected. There you go. Then you take this one up faintly. Right, okay. So we have got now, this is our 0.0 in terms of seconds. This is 120 seconds, okay? So each division there is representing 10 seconds, 10 seconds, 10 seconds times 12 divisions, that's 120 seconds. Right, we have got this point, that's 0 to 120 seconds. Right, if the direction is clockwise like that, which means our first point, this is 10 seconds. Right, that's 10 seconds. Right, then we have got 0, 10, 20, that's 30. Right, 40, 50, that's 60 seconds. Right, that's 90 seconds. Then this is 120, okay? Right, now if we check with regards to the specifications that we have, right? Let's try to position this. Right, with regards to the specifications, right, a rise of 70 during the first 30 seconds. Right, so we need that's 10, 20, right, you write here, 30 seconds, right, so that this should guide you. Right, a dwell for the next 20 seconds. Once it has reached this point, it will dwell, so it will be 40 and 50 seconds, right, from point 0, right, a drop of 30 millimeters during the next 20 seconds, right, so it has dwelled up to this point, it has risen from here to there, then dwelled, then a drop for 20 seconds, right, 30 millimeters, so you measure, 30 will be 60 and 70, okay, so you indicate 70 seconds like that, right, it should be dropping from here for 30 millimeters, which is this point. Right, a dwell for the next 30, right, that's 80, 90, and 100, right, 100 seconds, right, it dwells up to there, then drops to the minimum displacement during the remaining period, then it should come here. So let's look at this, right, in terms of the displacement graph. We are going to first of all rise for 30, like that. Right, then it dwells up to this point, then it falls for 30 millimeters for the next 20 seconds, then it dwells, right, which means it's not falling, then it returns to the minimum, which is like that. So that is our displacement graph. Then we outline. Let's outline using a red pen. That is the rise, then it dwells, then it begins to fall now, right, then it dwells, right, and it comes back to the minimum or the original position. So we have got something like this in terms of our displacement graph. Remember, the other critical element is to label, right? You need to label like that. You also need to label on this other side. Right, you also need to label this like that. Then you write nicely displacement graph like that. Then you write rotation in seconds. That is for 2 minutes, which is 120. Right, then scale. Right, the scale is given 120 millimeter is equal to 120 seconds. So 120 millimeter is equal to 120 seconds, like that. Right, that is the scale, right? Then here you write displacement. But remember, we said you can write displacement 1:1 or displacement in millimeter. Right, so that will be your complete displacement graph. The next thing, once you have done that, you have defined the direction of rotation, you have defined the movement in terms of your projections. So I'm going to just do this one and that one, and I want you to complete the rest as an exercise on your own. So this is from 0 to 10 seconds. So I'm going to do this, right? Remember we said this line is our line of action. Then from here, right, that is 20 seconds, which is here. Then from there, it will take us to 30 seconds. Right, the moment you have done that, you stand. That's your 10 seconds. So you describe an arc like that, a faint one. Then you go on to the line of action to 20 seconds. Then the 30 is already there. Right, so you connect this point to that point and that point, right, like this. So that is part of our chem disk. So I'm going to outline this. Right, outline that and even correct this like that. Right, so this is part of the chem disk. So what I want you to do, I want you now to complete the rest of the chem disk. Plotting from here, remember, once we have reached 30, from 30 to 50, which is 50 here, there is a dwell. Remember, let me just show you the dwell element. Right, do not use freehand for the dwell. You use a canvas like that. Right, so from 30 through to 50 seconds, right, you are going to make use of a canvas. So this is now part of the chem disk. I want you to complete the rest of the stuff up until you come here, projecting from the displacement graph. Hope you enjoy this exercise, and I wish to see you again tomorrow when we look at more tasks with regards to the chem. Thank you and good night.